Welcome again to my series on creating a game engine called Midpoint. In this video, we will begin with our landscape system and apply textures to it based on where the textures best fit on the landscape. It's really a powerful functionality which is partially enabled by the freemium tool Gaea. Here we begin our journey with Gaea. You can download the free version directly from their site. I am currently using version 1. This is just one possible landscape you could set up. But for our purposes, we will want a height map as well as two masks for the texture placement. For that reason, once we have a landscape we like, we add the rock map and soil masks as nodes at the end, and then mark the last three nodes for export, so they appear in the sidebar. In the sidebar, we simply set the height map to be a TIFF file, while the masks are best exported as PNG files. That's all it takes to set up Gaea for export. Go ahead and run the Start Build button to export your files. Now, let's build a simple U component which we can reuse later. This is basically a file input which sets the base 64 encoded data on a state passed via props. This essentially allows us to pass the file data around as a string. Inside of our file browser component, which we built in a previous video, we will want to add a tab for landscapes. This begins with a few of our file input components tied to some simple state for the base 64 and file name. Next comes the Save Landscape button, which actually puts these files in the correct spots. Of course, we enjoy some Rust verbosity due to Rust's ownership model. To finish up this button, we simply send all of the relevant data to the background process for saving and syncing. If we take a look at the Save Landscape handler in the background process, we'll see that each file type has its own directory. This will keep everything organized for our projects. As we continue, we have a very simple process at play. We create directories if they don't exist inside the sync directory. Then we simply decode and save the base64 data for each file. All of these files will be synced by a separate file manager app, which is covered in another video, and which will enable collaboration in our engine. Now we have the actual landscape grid. This is where we will feature landscapes that have been added. As is covered in the file sync video, once a landscape is added to the sync directory, it will be uploaded to OS/S3 in CloudFront, while a WebSocket message will also cause our engine to update this grid in real time. You can also find more information by checking out the GitHub and the code there. As you can see, we keep it very straightforward as this is still early in the engine's development. Here we have the add to scene on-click handler. You may remember the saved context and local context from previous videos. They are simple use states where the saved context is synced to the database and between all clients connected to this project, while the local context is only for this local session state. In this case, since we are adding a landscape to the scene and want that to be shared between everybody, we update the saved context. We also dispatch the selected component to the local context, which is only relevant to this particular user. Finally, we leverage the handle add landscape function in order to add the landscape to the wgpu scene. Now, in our wgpu code, we specify the add landscape function. Much like in the video on 3D models, we will pause our rendering as well as use the mutex guard, so that we can safely add the landscape inside a spawn process without creating an error during rendering. Notice the drop function as well, which is necessary for the guard. If we jump to the background process getLandscape pixels handler, it begins like many of our handlers. We specify the hard-coded sync directory as well as the particular directory within it where the height map is located. Then we use our read_tiff height map function to pull out the necessary data, which will be passed back to the U front end. Inside of the read_tiff height map function, we actually open the file and grab its initial metadata. Then we prepare a new vector to hold all of the pixel data. Since each pixel in our height map holds data describing a point in space, we can loop through the height and width themselves. The calculations are actually very logical. If you look closely, the IDX moves through each row based on y multiplied by width, while the location within a row is determined by adding x, thus yielding the IDX, which can be used to pull the height value. The other calculations are just as logical, but if you need a more thorough explanation, ChatGPT is your friend. Now, all the way back to our renderer state. This is where we define the addLandscape function. It just instantiates a new landscape struct and pushes it to a vector for render. Okay, here's a look at the actual landscape struct. This is, of course, a very critical portion of this entire setup. The key here is to notice the typical transform, buffers, and bind groups are associated here, just as they are with models or even basic cubes. However, we also specify the texture array, which we will use when applying textures to the landscape. When we begin our new landscape method, we find that we're simply pulling in our vertices and indices as usual and creating the relevant buffers. Simple. Next, we create our empty uniform buffer, which we use for our transform to determine its position in space. To wrap up this method, we just pass back what we have so far. We haven't added any textures yet. Now, if we take a look at the generate terrain function, you'll notice that we leverage the data prepared in the background process. We do that here so we can build our wgpu compatible vertex vector, but also so that we can prepare for in-game physics with Rapier. Rapier is not the focus of this video, but we prepare the necessary points for use later. Here, it's important to realize that without all of the needed indices, we will have gaps in our terrain. We use the extend from slice function to append the vector data to our indices vector. It looks complicated, but it's also very logical. First, we connect vertices to form the main triangle, as we normally would. Then we make sure that the triangles are properly connected as well, to ensure no visible gaps. Technically, that's all it takes to add the landscape to the scene. However, it wouldn't do us much good, as it would be invisible without any textures applied. I recommend building out a texture generation area, much like with the concept generation video, so that you can generate new textures conveniently in the engine. Anyway, here's the function in our wgpu code for adding a landscape texture. Much like with adding a landscape, we pause rendering and guard our mutex. Next, we use a couple helper functions to pull in both the texture and related mask, which was added with the landscape at the beginning of the video. Then we match the provided kinds and transferable string values. Then we leverage the update landscape texture function on our renderer state to do the necessary work. Here I share the helper functions for your reference, although it is mostly typical for our setup. If you need any code that is not shown in this video, be sure to check out the GitHub. Here's the other helper function. Now, if we check out the handlers on the background process, we will see some more code that is typical of our engines thus far. It's mostly self-explanatory, simply retrieving the bytes and some metadata. The mask handler is basically the same, although the path is different. Alright, so back to our renderer state. We need to add the update landscape texture function used in a previous handler. It simply adds the mask and the texture, supplying the respective kind and the needed wgpu objects. If we dive into the update texture function, you'll notice that each texture or mask gets a layer. This layer is used to specify a location in the texture array to hold the relevant data. The texture array is simply far more performant and ergonomic than using a texture atlas or sprite of some kind. Now, we write the texture into the texture array. As is common practice, the bytes are 4 multiplied by the number of values, while the rows could be equal to the height. In the case that the texture array doesn't already exist, we create it here. Finally, to wrap up this texture's functionality, we make sure to update the bind group with the latest texture array view. That's it. Now you should be able to add a landscape and even apply textures to it based on the Gaea masks. Of course, this means that textures are only applied to the relevant spaces on the terrain, resulting in a very realistic look. In the future, we will be able to touch up the landscape using brushes and textures that fit perfectly with those used here. I hope you enjoyed the video, and if you learned anything, be sure to subscribe. Thank you.